My name's Jieying Tan, and this is my science fair project presentation. So, here's the table of contents, and we'll start with the introduction. So, the aim of this project was to highlight the promising role of plant phytochemicals in combating antimicrobial. In doing so, we could provide insights for future in vitro and in vivo validation of identified compounds for potential therapeutic and potentially guide the development of novel antimicrobial therapeutics against multi-resistant bacterial infections. This project enforces the growing interest of using plant phytochemicals in combating resistance and highlights the potential of those plant phytochemicals as inhibitors of the enzymes involved in bacterial resistance mechanisms. So onto the background. Background. Antimicrobial resistance is the proliferation of resistant pathogens that lower the effectiveness of conventional antibiotics. It arises from genetic mutations that increase the pathogen's resistance to an antibiotic, tannins, saponins, and organosulfur compounds. Many exhibit potent antibacterial activities by inhibiting bacterial enzymes, disrupting cell membranes, interfering with quorum sensing, blocking efflux pumps, and suppressing biofilm formation. They are chemically diverse and have synergistic effects with conventional antibiotics. They have potential in combination therapies with conventional antibiotics and can lower the required dosage and reduce the likelihood of resistance development in pathogens in comparison with single-targeted antibiotics. Currently, plant phytochemicals are not completely understood. In vivo and clinical trials have also not been performed yet. For the methods, bacterial resistance mechanisms and protein targets are selected, as well as 30 plant phytochemicals. The 3 bacterial protein targets selected were subclass B1 metallo-beta-lactamase NDM1, aminoglycoside 6' N-acetyltransferase, and multi-drug efflux RND transporter ADE-ABC outer membrane channel subunit ADC. They were sourced from reports and research papers. Then bacterial protein targets were ran through P2 rank to identify pockets that could potentially be active sites. Since P2 rank predicted a pocket in multi-drug efflux RND transporter ADE-ABC outer membrane channel subunit ADC with a low binding probability of 0.001, the pocket wasn't considered an active site. After bacterial protein targets were visualized in ICAN 3D and interactions between their active sites were identified, excluding multi-drug efflux RND transporter ADE-ABC outer membrane channel subunit ADC. To prepare for docking, bacterial protein targets were cleaned with Chimera X by removing water molecules and adding hydrogens. For docking, bacterial protein targets and plant phytochemicals were docked once per target ligand pair in SwissDock. After, during data collections, screenshots were made of active sites and interactions of atoms in the active sites were noted in a table. Screenshots were made of the best docking poses, with their docking scores noted down into a table. The best docking poses had higher binding affinities, which meant a lower docking score. Aminoglycoside 6' N-acetyltransferase and multi-drug efflux RND transporter ADE-ABC outer membrane channel subunit ADEC. The active sites are highlighted in each figure. As mentioned, P2 rank predicted a pocket in this protein, but with a low binding probability of 0.001, so the pocket wasn't considered an active site, and the pocket isn't shown in this figure. So here are the tables of docking scores for each individual plant phytochemical and specific bacterial protein target. The first table here is plant phytochemicals docked with the subclass B1 metallo-beta-lactamase NDM1 bacterial protein target. The second table is plant phytochemicals stacked with aminoglycoside, 6' and acetyltransferase bacterial protein target. The last table here is plant phytochemicals stacked with the multi-drug efflux R&D transporter, ADABC outer membrane channel subunit, ADAC bacterial protein target. You can see that galantamine, gibberellic acid, and reserpine have the highest binding affinities or lowest docking scores across all tables. And the top two compounds out of all the tables were galantamine and gibberellic acid. The figures here show galantamine docked with the bacterial protein targets. A is the bacterial protein target subclass B1 metallic beta lactamase NDM1 with a docking score of -11.311. B is the bacterial protein target aminoglycoside 6' and acetyltransferase with docking score of -11.728. C is the bacterial protein target multi-drug efflux R&D transporter ADE-ABC outer membrane channel subunit ADEC with a docking score of -10.1287. Blue dashed lines represent hydrogen bonds, yellow dashed lines represent ionic interactions, orange dashed lines are cation pi interactions, gray dashed lines are hydrophobic contacts, and green dashed lines are pi stacking interactions. So the figures here show gibberellic acid docked with bacterial protein targets. A is bacterial protein target subclass B1 metallic beta lactamase NDM1 with a docking score of -9.1253. B is the bacterial protein target aminoglycoside 6' and acetyltransferase with a docking score of -9.8133. C is the bacterial protein target multi-drug efflux R&D transporter ADE-ABC outer membrane channel subunit ADEC with a docking score of -7.7184. So this project explored the inhibitory potential of plant phytochemicals against key enzymes in bacterial resistance mechanisms like beta lactamases, efflux pumps, and aminoglycoside acetyltransferases. Molecular docking of these enzymes or bacterial protein targets with plant phytochemicals showed that these phytochemicals exhibited strong binding affinities and could potentially inhibit these enzymes in bacterial resistance mechanisms. For example, galantamine and gibberellic acid. Interaction analysis between bacterial protein targets and plant phytochemicals revealed hydrogen bonds, ionic interactions, hydrophobic interactions, and more, which helped stabilize ligand and protein target binding. These results match what previous studies performed where plant phytochemicals exhibited antibacterial activity, likely through the same binding interactions. Phytochemicals mentioned like galantamine and gibberellic acid had high affinities across multiple bacterial protein targets and has the potential to inhibit bacteria with multiple resistance mechanisms. While these results are promising, there are many limitations of this project. Molecular docking can only predict ligand-target interactions and does not account for other factors. In vitro and in vivo studies also need to validate the efficacy of these phytochemicals. However, this project, while limited to using in silico methods, can potentially contribute to the development of therapeutics using plant phytochemicals and address the challenge of antibiotic resistance. The conclusion is that this project highlighted the potential of plant phytochemicals as inhibitors of key enzymes involved in bacterial resistance, and molecular docking analysis revealed that several phytochemicals exhibited strong binding affinities. Those phytochemicals form bonds and stabilize binding. The high binding affinities across multiple bacterial protein targets observed for some phytochemicals suggests that their potential to inhibit multiple complex bacterial resistance mechanisms. However, these findings are predicted in silico and must be validated through experimental assays, In the future, researchers should focus on in vitro antimicrobial testing, cytotoxicity assessment, and pharmacokinetic profiling for validation of these phytochemicals. While these findings are predicted in silico, they can provide a foundation for the development of plant phytochemical-based treatments to combat antibiotic resistance. I think the part where I get mentored by a PhD is it's pretty impactful since I'm pretty new to research and I don't really know what's going on, and it's helpful. My favorite part with working with the YRI was I think just overall working on a project together with a goal. It was fun to do so and collaborate.